Hi, and welcome to the next lecture unit in the Gaussian process lecture chapter, which is on how to obtain the Gaussian process predictive distribution and also on how to do this for noisy Gaussian processes. So far we have only learned how to sample from a Gaussian process prior. And this is kind of a little bit boring and unexciting from, a learning perspective, where obviously we are mainly interested in how to use the knowledge we have obtained through our training data to predict values at new test observation locations at new measurement points x star. And what we will now do is we'll investigate how to update our Gaussian process prior through observed data points, observed labeled data points, to get our hands at a posterior process and how to use these posterior processes to make predictions. So first of all, let's introduce a little bit of more notation for unobserved test data points. So as always, we will use our design matrix X for the feature vectors of our observed training data points, and we have of course also observed labels now at these training data points, and we will nicely and compactly organize them in such a vector bold F. And now let's assume that we are given or interested in one unobserved test point x star, and with unobserved I mean we do know the location of x star, but what we don't know is how the outcome looks like at x star. But we'll denote this unknown outcome with an f star, and we are now interested in inferring the distribution of f star given our location x star, given all of our labeled training data. Assuming that we have a zero mean Gaussian process prior going on with a certain covariance function small k, what we now do know is that not only this vector bold F here is jointly normally distributed, we also know that even if we add in to that vector here an n+1 component, so our f star, this is still jointly normally distributed. And we know how this normal distribution now looks like. It's still zero mean, and it has this kind of partitioned covariance structure going on, where here in the upper left corner we have our n times n covariance matrix capital K, and here we have these we have this vector k star, which is simply the vector of covariances between x star and all of the various training data points. And here we have k star star, which is a single number, which is the covariance between x star and itself, which is usually going to be 1. Okay, so given that f, our outcome vector f at the training data points, is observed, we can now apply the general rule for conditioning of Gaussian random variables and obtain the following predictive formula for the Gaussian for the predictive distribution f of x star. So this will look like this. And as this posterior is also Gaussian, we also know how the maximum a posteriori estimate looks like. So if we're only interested in a point estimate, you would take this guy here, which is the mean value of this Gaussian, and which is the point of highest posterior likelihood. And we would obviously use this as a point estimate for the prediction at f star. So how does this formula come about? So as always for Gaussian processes, it boils down to pretty simple linear algebra, which is all based on simple formulas known from the Gaussian distribution. So there's a general rule for how to condition on Gaussian random variables and compute their conditional distribution. So if we are given an m-dimensional Gaussian vector, z, with a certain mean vector mu and a certain covariance matrix capital sigma, and we now partition this random vector here simply into two groups, z1 and z2, and z1 doesn't necessarily have to be the first m1 variables. We can also reorder stuff, or we can basically reorder stuff and then pretend that they are the first ones, and then set z2 is this second group. So this, we can basically just partition all random variables of z into two non-overlapping groups. And then we also partition here our mean vector mu in also into the two corresponding groups. And we also partition our m times m dimensional covariance matrix sigma into these four blocks, where sigma 1, 1 is the covariance matrix of z1, sigma 2, 2 is the covariance matrix of z2, and these are the in-between covariances between all of the variables from z1 and all of the variables from z2, respectively. And we now can easily compute the conditional distribution of z2 given z1 through this formula here. And you should have all been exposed to this formula before, for example, through a course on multivariate statistics, or one basic course on statistics that which has contained the theory of the multivariate Gaussian will have surely also included a proof for this super useful formula. And we can now use this formula directly to apply this here to this situation, because we can now partition everything into these n variables for our training data and this one variable for our testing data point. And here, like I said, we can already also see this partitioning here in the covariance structure on this right-hand side. Now we just apply that formula and we arrive at this result here. By just directly plugging stuff in with no further, intelligence required and no further transformations. Let's now explore this a little bit more through a simple example calculation and also a bit through visualization. So assume we are given only a single training data point at the measurement location minus 0.5. And we want to make a prediction at a test point which is located at plus 0.5. Under a zero mean Gaussian process with a squared exponential covariance kernel, we can now compute here this joint covariance matrix between x and x star. So first of all, we know that the covariance of x to itself under the squared exponential is obviously 1. Also, same holds true for the covariance between x star with itself. And the more interesting part here is the covariance between x and x star. So we simply enter x and x star, so minus 0.5 and plus 0.5 into this little formula and then compute their covariance. And we are now furthermore assuming that we have observed the label at our training data point x with a value of exactly 1. We can now compute the posterior distribution by employing this formula as before. So we have to plug in k star. So k star is exactly this guy here, so just a single number. We have to plug in our matrix capital K, or rather its inverse. So k is simply this number 1 here. And if we invert this, it's still going to be a 1. And we have to plug in our outcome vector f, because we have a single training data point. That's also just a number, and this is also this one here. We plug that in. Now we are done with the mean component, and now we have to calculate the covariance component. So that's k star star, which is this one here, and we have to plug in k star, which is 0.61, inverse of capital K, that was the one here, and again the k star, which is still 0.61. And now we simplify these two formulas here, and we arrive at the predictive distribution of f star, which is now a one-dimensional Gaussian with this mean value and this variance component sigma squared. And we can also visualize this here on the next slides to make this even clearer. So let me start here on the upper right hand corner. So here I visualize this bivariate joint density between f of x, the outcome f of x, and the outcome f of x star. So this is this guy here, okay? Just have visualized this here. And down below here and up here, I've visualized the marginal distributions of f of x and the marginal distribution of f of x star. And we know that these are Gaussian, these are univariate Gaussians, because our GP is zero mean, they are centered around zero. And we also know the variance because the covariance of x with itself and x star with itself are simply just one. So these are basically standard Gaussian densities. And at the moment, there is no, conditioning going on. So the posterior process, we haven't computed that yet. But let's now start doing that. So we now assume that we have observed a training point, and we have observed this training point here, or this training label, at the position of x equals -5. Yeah, that was our training data point where we assume the label is present, and we have that available to us to now condition on this. Which means we have observed a sample value here from this marginal distribution of f of x. And furthermore, we now have information regarding this bivariate normal density. So we now know that we are kind of living in a world where fx equals 1. So everything that now stochastically goes on in this world must happen here along this line. And now we condition our bivariate normal density to this kind of subspace, so to speak. We condition on the fact that f of x equals 1, and that gives rise to this one-dimensional posterior density of f of x star, given the fact that fx equals 1. And this now transforms this marginal distribution of f of x into this posterior distribution. And we can now make a prediction from that posterior distribution. If we want to make us, either we are already happy with having our hands on this predictive distribution, or we can make a point prediction by choosing this point here of highest posterior density, which would be exactly here this tip of, or the location of that maximum here of that Gaussian posterior bump. And we can do exactly the same calculation for different values of x star. So we can do this for -2, -1, +1, +2, and so on, and derive respective posterior distributions for all of these points. And if you want to nicely visually summarize that, maybe a good idea is to draw this posterior mean function here, and also to visualize the posterior standard deviation. So what I did is I added and subtracted 2 times the posterior standard deviation from the predictive distributions, and visualized this by using, visualize this through this grayish envelope here. And we can also now generalize this formula for the posterior process by doing the same thing for multiple unobserved test points, maybe m of them in parallel. So the formula before, although in my example here I only used one training data point x star, obviously if you check the formulas again, there was no restriction at all for the number of training data points, right? So this also wouldn't really make sense, I guess. I mean, normally in machine learning, we have not just one training point available, we have multiple, we have n training points usually available, and the formula was already working for multiple training data points. Yeah? But so far I've only presented how this works for a single test data point, and usually this is kind of enough, right? Because this testing data point is arbitrary. So here I already kind of in a looping manner went over all possible test points that I kind of wanted to visualize in this little plot. But it can actually be beneficial to have a joint formula available for doing inference on multiple test locations in parallel. So assume we are given n of these testing locations, and again we assume a zero mean Gaussian process. Now we can do exactly the same thing. We can partition this thing here, or we can write down the joint distribution for the n-dimensional vector bold f and the m-dimensional vector f star, and this is still going to be jointly normally distributed with zero mean. And here this partitioned covariance structure where k star is not a single vector anymore, but it's going to be an n times n dimensional matrix, where we have here the covariances between all of the training points and all of the testing locations. And k star is going to be an m times m covariance matrix containing the covariances between the x star points with themselves. But the whole derivation now of the predictive distribution of f star follows exactly the same pattern as before. There's not a big difference, and I guess you can also see from the pattern of the formula that it really looks super similar. Our lowercase vectors k star simply have become a matrix, capital K star, and the same for this k star star here. But this formula now enables us to talk about correlations among different test point sets and also to sample functions from this posterior process, which is pretty nice. Let's talk about a couple of more properties of a Gaussian process. So many of the things that I'm mentioning now I've mentioned before, but we can make them now a little bit more explicit because we now have these formulas available for the predictive distribution. So first of all, we have said before that we assume that our observed training data are measured without any type of noise or error. And for that reason, we were content with creating a Gaussian process where all of the random functions exactly pass through our training data points. So a Gaussian process is actually an interpolator of our training data. And we can also now mathematically check that this is exactly true by simply entering here our training data as testing points too. So if we enter our training data points as test points, this k star here becomes simply the matrix capital K, and k star star also becomes the matrix capital K. And then we can simplify here this predictive distribution considerably by noticing that K and K inverse simply cancel out, and here the covariance component simply becomes the zero matrix. And this means we obtain as a result a degenerate Gaussian distribution with a zero covariance structure and a mean component of bold f. So this means we don't really have a Gaussian distribution going on here. We have like perfect knowledge and we are perfectly sure that the predictions at our training data points, if we use them as test data points for predictions, are exactly f without any uncertainty left. So these are exactly the values we have observed during training, which means our model function, especially our model mean function, actually, well, every function that we sample from this posterior process passes exactly through these training data points. We can also discuss a little bit more the Gaussian process as a spatial model. So we've done this before, so I guess I'll do this reasonably short. So we know that the correlation between outcomes depends on the distance between 2 points x and x dash, and that this correlation is modeled here through these covariance functions, for example, our squared exponential kernel. And near data points with high spatial similarity and therefore very, very small spatial distance enter more strongly now into this prediction function, which means if we compute a prediction, let's say, for example, at a certain location here, what that means is that we are basically forming a weighted average of the outcomes of these points closely in the vicinity of such a prediction test location, while these points who are very, very far away from this test location basically don't enter into this predictive formula at all. Well, mathematically they do enter, but they enter with a contribution with a weight of nearly 0. So if you look at this formula here, you can also nicely interpret this as if you are predicting at a certain test location, what you are basically doing is doing a weighted averaging here of this test outcome vector, where weights correspond to how far away your training data points are from this test location under consideration. What you can also see here, if you inspect the visualization of the posterior variance, is again this spatial property that directly on test locations, predictive variance is 0, and then it's very small if you move away a little bit from test data points, and if you then arrive at areas where there's basically no training data available, and you're very far away to any training data point, posterior variance is very, very large. So you have this bumpy surface of the posterior variance, which is very, very small around training data points and clusters of training data points, and very, very large in areas where you haven't observed anything. Good. So far for the interpolating Gaussian process. Now let's generalize this to noisy observations. So, as I've said, we implicitly assume that we had access to true function values at training time without any measurement noise. And I now want to, and for the squared exponential kernel, that implied that this covariance here between the outcome at location I and the outcome of location J is exactly 1. Hang on. For fully observed training observations. Now, and as a result, the posterior Gaussian process is an interpolator through all of my data points. Now, I want to generalize this a bit because in reality this is often not the case. Usually measurement error is present, and usually you want to create a regression model and not an interpolating model. Now, assume we have access to noisy versions of our true function values. So that means that our y, our observed outcome, can be modeled as f of x. Yeah? So this is the true function value, the unnoisy function value, so to speak, plus an epsilon term, where epsilon is also normally distributed with zero mean and an error variance sigma squared, which is usually unknown. And let's assume that f of x is still a Gaussian process. What we can now do is we can compute the covariance of yi, yeah, so the covariance between the observed values, the observed noisy values yi and yj, and write this down as the covariance of f of xi plus epsilon of I in relation to the outcome value at location xj plus epsilon j. So by just plugging in this definition here. Now we can use the usual rules of the covariance function. So we know that this is bilinear, and we can draw out these epsilon terms here, or take this guy here apart at these plus signs, and we arrive at a result where we have here the covariance between outcome at the ith location and the jth location, plus 2 times the covariance between the ith location and the jth error term, and the covariance between epsilon I and epsilon j. Now we can simplify this a bit, because this here is nothing more than the covariance, the covariance function evaluated at the ith location and the jth location. This is how we define this covariance function. This here becomes 0, because we can usually make the assumption that the error term here, epsilon, is uncorrelated with everything else. And we also make the assumption that these error terms are IID, which means this covariance between epsilon I and epsilon j will only be 1 if and only if I and j are the same. Yeah, so if you're talking about the variance of epsilon I, so to speak, but if epsilon I and epsilon j are different error terms, they will also be independent and therefore uncorrelated, and this becomes 0 then 2. And these two facts we can simply abbreviate by using here this Kronecker delta symbol, which is exactly 1 if I and j are the same, and 0 otherwise if I and j differ. So we can now derive that the covariance between these two outcomes here can still be written as our kernel function k on the ith and jth location, but we have to add this sigma squared times the Kronecker delta. And the sigma squared term we'll now, for historical reasons, call a nugget. And we can also now derive the predictive distribution for the case of noisy observations now. So the prior distribution of y, assuming that f is modeled by a Gaussian process, is then simply a normal distribution on this y vector here. As always, usually this m here is a zero mean, and we have our covariance structure here, which is simply our matrix capital K, so our kernel matrix, plus sigma squared times an identity matrix. And this here is basically what we did on the slide before, just in matrix notation. And again, we can now write down this joint distribution between the observed outcomes y and, be a bit careful here, the vector of true unknown function values f of f star at a bunch of unobserved test locations. So here we are not using the y because we're not interested in inference for the noisy versions, but we are interested in inference on the non-noisy versions, which are these f's. And again, we know this is normally distributed. We also know how the covariance structure looks like. It basically looks like as before. The only difference is that here in this upper left corner, we don't have the covariance matrix capital K, which would be the covariance matrix for vector bold F, but we have these noisy versions, so we have to write down the covariance matrix for those, which is simply K plus sigma squared times the identity matrix. And now again we can go through these motions of conditioning or computing the predictive distribution of F star conditioned on these guys Y here. And this is again applying the same formula for conditional distributions for Gaussians exactly as before. So I'll not read this out. Basically obtain exactly the same pattern as before for the non-noisy case. The only thing that's different is before, or instead of having this capital K here in the middle, we have capital K plus sigma squared times the identity. So we add this sigma squared term to the diagonal of that matrix capital K, and again here. And you can also check that this easily converts back to the noise-free formula if you simply set sigma squared to 0. Of course, now this noisy Gaussian process is not an interpolator anymore. It's a true regression function where this mean function here is truly a regression that doesn't pass exactly through our training data points anymore. And the larger we make the Nugget term, the wider these bands, these noise bands or uncertainty bands become around the observed training points. And if you're wondering, well, do I have to kind of pre-specify this Nugget term now? No, you can also estimate this during training, and I will show you later how this works when I will also discuss how to estimate the covariance function hyperparameters through Gaussian process training. Okay, few final words on decision theory for GPs. I'll keep this super short. So until now, we really haven't talked about loss functions as we did before when we said that nearly every machine learning model is kind of optimized with respect to this loss function and tries to drive down this empirical risk. So Gaussian processes I kind of introduced through this Bayesian perspective, but we can still make use of such a loss function and minimize the empirical risk with respect to a certain given loss function. So how do we do that? It's actually pretty simple. So the theory of GPs gives us access now to such a posterior distribution of Y given our training data D. And if you want to make a prediction at a test point X star, we now have this complete posterior distribution available to us. Yeah, it's not a simple point estimate. We have this complete univariate distribution available to us. And if we now want to talk about a loss optimal point estimator at that location X star, we can calculate that by kind of integrating out over the complete distribution with respect to this loss function here, and then picking a certain prediction that's optimal for this loss function. So we simply write down here the risk of a point estimator Y star given that we are at the location X star, and this is just so the risk of a certain point, certain outcome prediction Y star is simply here this integrated loss where we kind of compare Y star with all potential points Y star and integrate out over the predictive posterior density of our process at the point X star. And now we just minimize this here, just pick the best point under this loss function, and are then basically done.